Welcome, Soc 350 class. This is April 6, 2020, a lecture on linear bivariate regression. This lecture is going to focus just on the second half of the Krieg text, chapter 10. We will wait until next week to start the Allison book, which focuses on multiple regression, but I wanted to give us a good grounding in linear bivariate regression and the logic of regression before we start adding additional independent variables into the mix. Linear regression is based on the idea that the relationship between two variables is linear as opposed to curvilinear. And we will come back and deal with issues of curvilinear relationships perhaps later in the semester when we talk about some nonlinear regression models and some alternate regression models that we can use. It also makes an assumption that you can draw that best fit line that we talked about last week when we talked about correlation and introduced the idea of correlation and regression, that you can draw that line, that best fit line on a scatter plot of that data. Regression analysis extends what we did last week with correlation, which tells us about the association between variables, to talk about how much influence the independent variable has on the dependent variable. So it allows us to describe the amount of change in the dependent variable that is accounted for by changes in the independent variable. And this is also connected to, as I said, the creation of that best fit line that I described last week. So let's look at the differences between correlation and regression and how these two statistics are connected. Correlation is a symmetric measure, as we talked about last week. It doesn't tell us about cause and effect. It doesn't tell us which variable is independent and which is dependent. If you switch which variable is X and which variable is Y in the calculation of correlation, it doesn't change anything about the calculation or the outcome of that calculation, because it doesn't tell us about the nature of that relationship, the causal relationship or connection between those variables. It just tells us that as one variable changes, the other variable changes in a predictable way. So that's what it's measuring, is how well we can predict Y by knowing X, or how well we can predict X by knowing Y. But it doesn't give us any information about which variable is causing change in the other variable. It's just looking at how changes in those variables are associated with each other. So regression, however, is a directional measure. It can tell us how much effect our independent variable has on our dependent variable. And this makes it very powerful. So for example, suppose we want to look at the relationship between studying and course grades. Correlation can tell us that the two are positively related. The students who spend more hours studying perform better in the course. But we could also interpret this as students who do well in the course spend more time studying. Remember, we don't have that causal connection, one causing the other. We just know they're associated. Regression, however, can tell us how much each extra hour of studying changes or improves or affects our course grade. So it can actually tell us it can give us a sense of how much change in the independent variable, how much a change in the independent variable can change the dependent variable, how much impact that it can have. Regression is distinguished from correlation in that regression provides us with a slope measure. So that is a sense of how many units of change in X it takes to create a unit change in Y. It does this by specifying an equation that explains the relationship between an independent variable and a dependent variable. And correlation can't do this. We talked about that. It can only tell us the strength and the direction of the relationship. Regression gives us a sense of causation, how one variable affects the other. So with regression, we're measuring how an independent variable affects a dependent variable. The basic formula for a line and for a regression line is Y is equal to A plus BX. And the slope in here represents the effect that a unit in the change on Z will have on the dependent variable. So B is our slope measure. And we'll come back to explaining what this means a little bit more. This is a very simple equation. Most equations are not going to be this simple. But it will give you an idea of why we would be interested in using regression. So let's talk about each component of this formula. So Y is the value on the x-axis that we're trying to predict. So that's our dependent variable. So that's what we're trying to predict. X is the value of the independent variable. A is what we call the y-intercept. So that's the value of y when x equals 0. And think about mathematically why it would come out that way. So if x equals 0, then b times x would be 0, and we would have y is equal to a, whatever that a value is. So when x is 0, y is equal to a. That's our intercept. That's where it crosses the y-axis. And I'll show you this visually in a minute. B is what we call the slope coefficient, which is also known as the rise divided by the run, okay? So here let's take a simple example. Y is equal to 12 plus 2x. So we can say that for whatever value x is, y is going, so what this would mean that for every unit change in y, there are 2 unit changes in x. For example, income increases $1,000 per year for every 2 years of education a person has. Now 12, this y-intercept is the baseline. That's the minimum salary, right? So that's the income or salary for 0 years of education. So when x equals 0, y equals 12. Now, nobody's going to get a job with 0 years of education. That's okay. That doesn't have to make any sense. So if we wanted to measure what affects income, we would look at something like education. Now, multiple regression is going to give us a little bit more information because most equations are not this simple, and we're going to want to look at multiple factors because we know that education is not the only thing that affects someone's salary, right? There are other things to consider, things like race, gender, occupational prestige, age, and so on, in addition to education. But this example gets us a sense of how this one variable, this one independent variable, does have an effect on the dependent variable. So how much education is going to impact income or salary. Okay. So given our equation of y equals 12 plus 2x, let's plug in some numbers and see what that would mean in terms of salary outcome. So let's run through a few examples. If someone has 12 years of education, how much would they earn in our equation? So we plug it into our equation, which is y is equal to 12 minus 2, or 12 plus 2x. So we plug 12 in here, which is our years of education. And so we have y is equal to 12 plus 2 times 12. Y is equal to 12 plus 24. Y is equal to 36. So this person makes $36,000. A person with 12 years of education makes $36,000. What about for 13 years of education? If someone has 13 years of education, we start with our same formula. We plug in 13 here for 13 years of education. And we find, when we do our calculation, that y is equal to 38. For someone who has 13 years of education, their salary is $38,000. And we can see that 1 year of education difference between 12 and 13 added $2,000 to the person's income. So that's what this is telling us. This value here is telling us that for every change in X, we get a 2-unit change in Y, right? So we add 2 to Y. What about 8 years of education? Plug it in again. So now we have 8 here, so 12 plus 2 times 8, which is 12 plus 16, or $28,000. One more. How about 16 years of education? Plug in our 16 here into our formula for the value of X, and we find the value of Y is $44,000. So someone who has 8 years of education earns $28,000. Someone who has 16 years of education earns $44,000. Okay. Now notice that between 8 and 16, we're not doubling the salary because the formula doesn't tell us to double the salary. It says to take the value of X, multiply it by 2, and add it to 12. Okay, so that's why we're getting what we're getting. Okay, so this is what our data would look like on a scattergram if we plotted those particular salaries that we just talked about as the example. So each point represents one piece of our data from the last slide. So an individual who has 8 years of education here, 12 years, 13 years, 16 years, and then I added 20 years as another example to show that. And so this is the formula for our line. Y is equal to 2x plus 12, or 12 plus 2x. This has it reversed. On Excel, it puts the A value at the end. Okay, so this is our equation, and this is what our line looks like. And over here is our y-intercept, right? So this is that value where, let me change the color here. This is the value of y where x equals 0. And we calculated that out, and we found that that was 12, right? So that's why our A value here is 12. So when x equals 0, the salary equals 12, or y equals 12. All of our data is in a nice little row. That never actually happens. So we never have data that perfectly, where every data point is on our best fit line. What we typically see is some things that don't fit so nicely. Remember that the regression line is, through the data, is the best fit line. And so that's sort of the one that minimizes the deviations around the mean. And we talked about, minimizes the deviations around that mean line. And we talked about that when we talked about correlation and introduced the idea of that. So note where it crosses the y-axis. That's our y-intercept point, as I said before, and that's $12,000. So in our case here, there's no error in our data. There's no error. But in real life, there would be error. And data that didn't, and that would be data that didn't perfectly fit on that best fit line. So most scatter plots don't look like that one. In the previous slide, all the data points fit perfectly on the line, but that's not what really happens. In real life, every data point wouldn't fit perfectly on the best fit line. Maybe it would look like this. There would be error. And the spaces between the dots and this best fit line, so the spaces between here and here and here and here and here and here, those represent error. And our equation has to be adjusted to take into account this error. So we're not going to spend too much time today talking about our adjusted formula that includes that error component, but I do want you to be aware that our best fit line is that perfect line that fits through that data that minimizes those deviations. But every bit of this, each of these pieces represents error. So this space here, each of these measures represent error or deviations around that best fit line. Now the best fit line is the one that does the best job, right? Minimizes that error. So our equation has to be adjusted in order to take into account that error. And as I said, we're not going to talk about, or we're not going to do the computational pieces on finding that error measure, but I do want you to know that there is that measure because everything doesn't fit perfectly on the line. So the formula, our revised formula for the regression line would be y hat. So this little hat over here on the y, that means it's a predicted value of y is equal to a. That's our y-intercept, plus bx, which is our, b is our slope, and x is our value for x, plus e. This is our error term. So that represents, the error term represents the amount of salary that cannot be explained by the number of years on the job. So, or that it, by education, excuse me. So it would be what we don't understand, what isn't explained by how many years of education that someone has.